Right. One thing that's come to my attention is a few people have lost problem sets completely. That is, that they completed them, they answered the questions, ideally submitted them to be graded, which is a bug in the website. You have to press that button. I can see the answers with or without that button being pressed. But then things completely disappeared. I encourage you to check your problem sets, make sure that all of them that you did appear, the questions appear answered. If they vanish completely, let me know. I'll work on it. But yeah, the website, along with having some functionality problems, it's got some bugs. Yeah. You can't even view them? Nothing about them. Yeah, I know you can't, if you don't press finish assignment, you can't go, you can no longer press finish. I might just like extend the deadline for all of them so you can go back and look at them and make sure you've answered all of them. Note to self, I'll do that. Any other class structure issues that I should be paying attention to? As I said about Orion, I'll be very lenient about giving full credit for a decent attempt at a decent number of questions. Somewhere in the mid-100, 100 to 200, between 100 and 200, you're good. Any chapter. All right? Lots of trouble with websites. In talking about nuclear power generation, I never talked about the attempts currently underway to try to eke power out of fusion rather than fission. The existing nuclear power plants are all fission-based, breaking the big nuclei down into smaller pieces, a process that releases energy. There are efforts to use fusion, the building up of small nuclei, to release energy. Basically, all the nuclei ideally would evolve towards the middle ground, which is around iron. So the little nuclei, putting them together releases energy because the strong force, the nuclear force dominates. The big nuclei taking apart releases energy because the electrostatic repulsion dominates. In the middle ground, you've run out of energy. Anyhow, using fusion to generate power is really hard because the nuclei do not want to go together. They're positively charged. Getting them to touch and stick is really tough. And the two approaches currently being studied approximately are magnetic confinement, which uses an effect that I've never talked about this semester, or not really, that charged particles spiral around magnetic flux lines given the opportunity. This, incidentally, is the origin of the auroras, the North and South Pole, that charged particles from the sun, when they get in the Earth's magnetic field, spiral around the magnetic field lines, which are particularly present at the North Pole and the South Pole, and that spiraling and then hitting things causes them to glow. So the spiraling is an interesting effect for many reasons. And you can get hydrogen nuclei trapped around magnetic flux lines. And why do that? Well, it's so you can get a plasma of charged hydrogen nuclei at tremendous temperature inside of a bottle that's at room temperature. I mean, how do you do that? If you allow these things to come into thermal equilibrium with the bottle, they will cool off and you won't get any fusion. So they have to get very hot stuff away from the walls, and they do it ideally with magnetic trapping. It's really tough. These projects have been going on for decades, and they'll be going on the rest of your existence in all likelihood. Who knows whether they'll ever succeed in getting enough nuclear fusion to occur in these environments to sort of pay for the power that goes into the machine. You want to get more power out than you put in. The other approach is to take hydrogen targets and blast at them with lasers, and try to crush the hydrogen down to high temperature and density, to the point where you basically you get a small thermonuclear explosion. That's also really tough, and the experiments on that have been going on for decades too. So these are just sort of ongoing projects. Who knows whether they'll pay off. They're quite expensive. They're part of sort of public policy decisions, but on they go. Any questions about those thoughts, ideas? Just for show and tell, this is a liter or a kilogram of heavy water. So it's like ordinary water, except all of the hydrogen in it is deuterium. It has, instead of a single proton as the nucleus of all the hydrogens, it has a neutron and a proton, a deuterium nucleus. So, I have it, it's handed down to me. I'll probably hand it down to somebody else. I've never managed to find a use for it in my lab. It's about $1,000 worth. So, yeah. Oh, yeah. Right. Yeah. All right. You look it up. If you look up the chemical catalogs, it's about $1,000 a kilogram. Selling it by, yeah, that's good enough. All right. On to medical imaging and radiation. So the goals of this are to look at how X-rays image things. So X-rays and their fancy computed version, the CT scans, how do those work? How does radiation therapy work? And finally, how do MRI imaging work? So that's my plan. And I'll ask this question, which is actually quite similar to one in the problem set. X-rays have trouble going through lead because why? If you've ever had an X-ray, you may well have been shielded in a garment full of lead. You know it's lead because it's really heavy. How many think it's because lead is a metal? How many think that it's because lead is heavy, that it's a good shield? How many think it's because lead atoms have many electrons? Hey, good. Yeah, that's it. Okay, because lead is a hard material. It's not. It's a pretty soft material. So it's the many electrons that do the trick, and we'll come to that shortly. Some observations about medical imaging and radiation. They go right through your skin somehow, so obviously you're not impenetrable. Something's going in there. The imaging involves radiation of various sorts, but the distinction actually is important and worth knowing, because not all radiation is dangerous. Some of the imaging radiation is hazardous, some of it's not. Radiation in general, the radiation that is hazardous can be used in ways strategically. You don't use it willy-nilly, but you can use it to do good rather than bad. Some of it involves radioactivity, and some of it involves accelerators. So the questions I'll go through, the first is just how do you make X-rays? And then finally, why do they image bone rather than tissue? So how do you make X-rays? And first of all, I should just remind you what X-rays are. They're just part of the electromagnetic spectrum. And so the whole semester, we've been working our way through it. We started with radio waves, which are the lowest frequency category of electromagnetic waves. Low frequency, long wavelength. We then worked our way up to microwaves, which are higher in frequency and shorter in wavelength. The wavelengths get shorter than a meter. We then encountered infrared light, and there's something called millimeter waves in there too. So you get infrared light, then you get into the visible, the Roy G. Biv visible portion of the spectrum, which is just a tiny swath of the electromagnetic spectrum. And then you get into ultraviolet light. And after ultraviolet light comes X-rays. And after X-rays, the categories, and just naming things, it's the same phenomena, is gamma rays. So that's the whole sweep of the electromagnetic spectrum as just given names. All right? And as you work your way through this, if you recall, the discovery in the world of quantum physics was that frequency and energy go together. So these are waves, yes, but they are emitted and absorbed in their packet form, in their particle form, as photons, little doses of energy, and the higher the frequency, the more energy. So the energy in a radio wave, photon, tiny. It's low frequency. There's not much energy in it. Microwave, a little more, still tiny. Off into the visible light, now there's enough energy per photon to be vaguely interesting. Interesting enough that your eye can sense it chemically, but doesn't cause you much damage. Maybe the blue end of the spectrum a little. Ultraviolet, now there's enough energy in each photon, each quantum of unit of the light wave to do chemistry, and real serious chemistry, and even to throw an electron out of an atom or a molecule. And so ultraviolet light's a little dangerous. And this is why you don't really want to roast yourself with it. It's not a thermal damage, it's a chemical damage. I think using the word roast is a little not right. It's not heating you up, it's just going into individual molecules and just busting them, okay? You can notice this by the bleaching that ultraviolet light from the sun does of things. You leave stuff out in the sun for a while and the colors go away. That's chemical damage being done to the color molecules. And then beyond ultraviolet, you get to X-rays. Whoa, those carry a lot of energy per photon, and they can do some serious chemistry and damage to molecules, even more than one. And then gamma rays, they're big-time packets of energy, do a whole lot of stuff. All right, so how do you produce X-rays? These high-energy photons, very high frequency, very short wavelength. And the answer is there are two approaches. That's what it's saying. The two classic approaches are these last two entries on this slide. One is the very, very rapid acceleration of an electron. And I'll talk about how you get that unbelievably fast acceleration of an electron. It doesn't happen by driving electrons up and down an antenna. You can't do it that fast. And then the other is really energetic radiative transitions in atoms. We've seen that if you put energy, for example, into neon atom, you can get an electron in an excited orbital that then jumps back to its original orbital, and in the process gives out red light. Well, in big atoms with lots of electrons around, you can get jumps that are much bigger than red light. You can get jumps that are all the way into the X-rays. But you need complicated big atoms to do that. Big not being geometrically big, but full of structure, lots of electrons, and consequently lots of positive charge in the nucleus. So the two ways in which the X-rays, if you've ever had X-rays, which is dental X-rays, all these, they come from two sources simultaneously to some extent. One of them has this fancy German name, Bremsstrahlung X-rays. And Bremsstrahlung X-rays are produced when you take a very fast moving electron, really whizzing, like from a very high voltage, 50,000 volts or 100,000 volts. If you looked at the dials on your dentist's X-ray machine, for example, you'll see they get to choose the energy, I think, and it's typically 50 kilovolts, 100 kilovolts. So that's the amount of voltage across which the electrons are accelerating. So they're carrying with them their 50,000 to 100,000 perhaps electron volts of energy. Remember, electron volts is this teeny tiny unit of energy associated with it's the energy that one electric charge gets in moving across 1 volt difference in voltage. Anyhow, you go really fast electron, send it into a material, and particularly a material that has big nuclei, lots of positive charge, and have that electron come very close to one of those nucleus and whip around it. Because it's positively charged, the electron's negatively charged, the electron loves that nucleus. Whoa! And it's like an amusement park ride where you're whipped around a corner really fast. That's a tremendous acceleration. And it's big enough that it can produce an outgoing electromagnetic wave that carries much of the energy of the electron, a good fraction of it. There are statistics to the whole thing, but you can get from that 100,000 volt electron with 100,000 electron volts of kinetic energy, you can get an outgoing electromagnetic wave with nearly 100,000 volts, electron volts of energy in its photon. Really high frequency, high energy outgoing wave. Is that okay as an idea? It's the old story that accelerating charge emits electromagnetic waves. In this case, really rapid acceleration emits a really short wavelength, high frequency electromagnetic wave, an X-ray. Okay? So that's where a lot of the X-rays come from in any X-ray you've ever had. The other is the characteristic X-ray. This occurs when one of those electrons being shot into a target, really. The target is typically something like tungsten, a metal that's hard to melt, which is important because this dumps a lot of thermal energy into the target. And it's a big nucleus with lots of positive charge. So the electron can whip around the nucleus and emit Bremsstrahlung X-rays, or it can go into the tungsten atom and knock an electron. You know, it hits an electron, knocks one of the electrons that was happy and sitting in the tungsten atom, knocks it out. Wow, it's gone. And what happens, another electron drops into that empty orbital. Suddenly there's an empty orbital. And electrons love to settle into the lowest available orbitals, these standing waves in the atom. They're around. So as it drops, as one of the electrons, typically one of the ones on the periphery of the atom, out there far from the nucleus, goes, wow, there's a better place for me. You know, seat's empty up there in the orchestra. So it will drop into that seat. And in the process, it will do a radiative transition, just like in neon, from one orbital to another, emitting red light in neon. In this, one orbital to the other, poof, out goes a characteristic X-ray, an X-ray corresponding to the difference in energy between these two orbitals. And now it's in the X-rays. Really high energy transition. Okay? So nothing much new, except it's here's a mechanism that produces really high energy photons rather than just the ones that glow prettily in a discharge lamp. All right. The spectrum of electromagnetic waves coming out of, and of course I didn't bring my, I was showing people things with my laser pointer, so now I've got a non-laser pointer. It's pretty useless. All right. If you look at the spectrum, there's a statistics. This is energy in the X-ray photons, and this is how many of those photons there are. The low energy X-rays are actually more abundant, and they fall off almost linearly with energy. And at the highest energies, which are approaching the energy of the electrons that were being fired at a target, there's not much left. Just to back away and say, what does an X-ray tube look like? It's a vacuum tube that has nothing inside, no air. Get the air out of here. It's got a source of electrons that puts the electrons into empty space. How do you do that? Well, for example, you heat up a wire so hot that the X-rays sort of boil off of it. Electrons boil off of it. You get electrons, it's called thermionic emission. You get electric charge coming right off of a hot metal. The thermal energy does the trick. Once they're in the empty space, you attract them to positive charge. So you have a piece of tungsten at the other end of this empty space that's at positive 100,000 volts. And those electrons go, wow, this is good. They hit that tungsten, traveling like crazy, and they emit this sort of spectrum of electromagnetic waves. It reaches a minimum, almost no intensity, at where the X-rays are carrying all of the energy each electron had as it hit the tungsten target. Because it just got statistically unlikely, and in physics also, it's unlikely that all of the electron's energy will go into one photon. It's just too hard for that to happen. But as you go to look at lower and lower energies, you see more and more photons coming roaring out of this tube, and it keeps on going up to sort of light, visible light, for example. There's a little bit of light coming out of this thing. The peaks in here, the spikes, correspond to characteristic X-rays. Those are the ones that happen not because of Bremsstrahlung, the whipping around the nucleus, but rather because of the radiative transitions from orbital to orbital. So there's specific spectral lines, just like there's spectral lines for neon. And in this trace, the low energy X-rays coming out here and heading off into ultraviolet light and so on, they're cut off. Why are they cut off? Because the tube has a window on it. It's a vacuum tube after all. And to get the X-rays out of the tube, they have to go through the window. And the window is deliberately designed to stop the lowest energy photons from getting through. Why? Because they're no good for imaging. They don't have enough energy really to get through you and do anything interesting. Instead, they get absorbed too close to your skin and they burn your skin. So the early X-rays, way back when, before people figured out you need a window like this, you get a lot of skin damage. serving no good purpose. So they now put a filter in there to get rid of the low energy X-rays. Okay? Any questions about how to produce the X-rays then? Fast moving electrons, out go X-rays. You hit a target, out go X-rays. Okay, why do X-rays image bone rather than tissue? And this has to do with, and it's worth knowing that, because you will, in all likelihood, you or somebody you care about will be in a situation of needing imaging, looking into you without like slicing you open. How are you going to do it? Well, the two classic approaches are X-rays and variations on X-rays, and magnetic resonance imaging, formerly known as nuclear magnetic resonance imaging, but they've dropped the word "and" because it's scary. Anyway, they image completely different things. They're totally different approaches, different pluses and minuses. It's worth using the right one, or at least knowing which one's which. So in X-rays, the idea is you send the X-rays into somebody, we've seen how you make them, and you cast shadows. They cast shadows, particularly, it'll turn out, of large atoms. Atoms, big atoms. Again, that's jargon. Atoms with lots of electrons. We'll see why. When those X-rays go into material, they got so much energy, they're interacting with individual atoms. They're really in there looking at the atoms. And they're interacting with the atoms' electrons in two ways, primarily. One is by Rayleigh scattering. We know about Rayleigh scattering. That's the blue sky. If you remember, little particles in the air were big enough. They weren't big enough to be good antennas for visible light, but they're tolerable antennas for at least the very blue end of the visible light with the short wavelengths. And so the blue light gets scattered. If you go through miles of air, you get a little bit of blue light scattering, enough that the sky glows blue. X-rays have a much shorter wavelength than visible light. And so their wavelengths are getting on the order of atomic sizes. So atoms are pretty decent antennas for X-rays, meaning there's a lot of Rayleigh scattering going on, where the X-ray comes in, jiggles the charge in the atom, and particularly the electrons, and the X-ray gets absorbed and re-emitted in a new direction. So Rayleigh scattering is actually around a lot during X-rays. It is a nuisance. It's not good for imaging. It just gives a general glow and doesn't give you, you don't know where they came from. It's like you can't tell what the sun looks like or any shadows by looking at the blue sky. It's just blue, just light from everywhere. So they deliberately try to get rid of scattered light in the imaging process. They actually will image through pipes that make sure that the X-rays aren't ones that were skittled around, bounced off things by Rayleigh scattering, and worked their way to the detector at cockeyed angles. They want the ones that went straight through, or not at all. So Rayleigh scattering, problem. The photoelectric effect is the main effect that allows them to image parts of you. What happens in the photoelectric effect is an atom with its electrons was just sitting there, and the X-ray comes in and provides enough energy to toss an electron right out of the atom, gone. It just heads off into the distance. And that's called the photoelectric effect. Photon in, electron out, photoelectric. And that effect has rules about it and statistics, and it turns out that it's most effective at absorbing the X-ray and kicking out an electron when the outgoing electron goes out with a modest energy. Not zero energy, not a huge amount of energy, but just a medium amount. So that X-ray comes in with a tremendous amount of energy, and it looks at the electrons, in effect, and the electrons that are weakly bound to the atom, ones that are easily removed, it doesn't remove them. Because if it did and used all of its energy, which that's its only choice, all or nothing, if all of that X-ray energy goes into one of these weakly bound electrons, that electron will go out with a huge amount of extra energy. It took a tiny bit to remove it from the atom, and the rest goes into kinetic energy. That electron will go off at ferocious speed, approaching speed of light speed. That doesn't happen. It's very rare. Instead, what the X-ray wants to do is it wants to encounter an atom that is big enough that it has a lot of electrons some of which are quite tightly bound, and it takes a lot of energy to remove them from the atom at all. And the X-ray ideally has just enough energy to remove that electron and give it a modest amount of leftover. That's when it occurs most strongly. So in a complicated atom like calcium or phosphorus, let's stick with calcium. Calcium's got 20 electrons. If you choose X-rays in about the right range so that they have enough, choosing the energies, you want X-rays that have enough energy to remove some of calcium's most tightly bound electrons and send those off with modest energy. That's the ideal. So calcium is just complicated enough to handle these X-rays. Atoms that are smaller, that have fewer electrons, and they're less tightly bound in there, they can't handle this X-ray anymore. This X-ray comes along. It might be 50,000 volts. I don't know, somewhere in that range. It comes along, and it looks at, for example, an oxygen atom. Oxygen has eight electrons. Not enough. That X-ray, if it goes after oxygen's most tightly bound electron, it will throw that electron out with huge energy left over, and so it doesn't happen. So the X-ray ignores oxygen. It ignores most of the elements from which tissue is made out of. The classic four that are organic molecules: hydrogen, tiny atom, easily removed electron. It can't stand X-rays. There's way too much energy for it. Oxygen, nitrogen, and carbon. They're all relatively small, simple atoms, not a lot of electrons. They can't handle X-rays. An X-ray will come in, tear out their most tightly bound electron, and throw it out at nearly the speed of light. It's not going to happen. You need a complicated atom like calcium to really get the attention of the X-ray, absorb it, throw out an electron. So that's why X-rays pass relatively easily through tissue, apart from the Rayleigh scattering problem, and come out the other side. But if there's a bone in there, when they encounter the bone with all the calcium in it, they tend to get absorbed and throw electrons out inside your bone. Nothing much happens, but the X-ray's gone. So your bones cast a shadow in an X-ray illumination of your body. You put an imaging device on the far side, it's going to see bright light, bright X-rays coming at it through tissue, but if there's a bone in the way, it's going to be attenuated X-rays, partly absorbed. Is that okay, people? So you're imaging primarily by way of that photoelectric effect. You're looking for big complicated atoms. If you're imaging things other than people, for example, welders will image welding, pipeline welding, for example, where it really matters you did it right and got everything clean and neat inside. They will actually X-ray it. But they will use X-rays that pass through bigger atoms than people. So instead of using these ones that we're exposed to with energies in the 50,000 volt electron volt range, they'll go to 1,000,000 volts or something, enough that the X-rays are able to go through steel, iron atoms, and which are bigger atoms. Iron, I should know how many electrons, but it's a lot. Okay, so a human X-ray machine won't see much through trying to look through metal work, but a more higher energy X-ray system can see through it and image the quality of welds, for example. Okay? Something like lead is just really nearly impenetrable to X-rays of the type used for imaging us, because there's so many electrons in lead that there's surely some that are capable of absorbing almost any X-ray you choose and absorbing it and then leaving with modest energy, exactly what the photoelectric effect prefers. All right, so that's why you wear lead shielding when you're being X-rayed. All right, the Rayleigh scattering I've talked about, the photoelectric effect I've talked about now, and so this is just my drawing of that effect. And so the window of the X-ray tube. Remember, I talked about the goal of this window is to let through the high energy X-rays for use in imaging you, or approximately, and blocking the low energy stuff that it doesn't even qualify practically as being X-rays, but it would just burn your skin. So you want to block that low energy stuff, but let through the high energy stuff that will image bone. What material do you want to make the window out of? Everybody okay with the question? How many think you want to make that window out of tungsten? How many think you want to make it out of copper? Iron? Aluminum? It's aluminum. Sure enough, X-ray tubes typically have aluminum. It's got enough, it's sturdy enough you can make a real thin aluminum window that's basically opaque to all the nasty burn your skin, low energy things. But the high energy ones, they go right through it because aluminum not enough electrons, it can't figure out how to deal with one of these humongous X-ray photons. Go by, go by. All right. So there's the X-ray image. Casting the shadow I've already talked about. And I talked about lead, right? This is the original question. You all got it right in the beginning. Lead has many electrons. That's why it blocks a vast variety of X-rays and so on. CT scanning, which has become more common and popular as time has gone on, it's just glorified X-rays. It's still, you got an X-ray source, maybe more than one, and lots of X-ray detectors. And the idea is basically you take an X-ray from a whole bunch of different angles of the same person. So the X-ray machine sort of goes around you. And the idea is that you get lots of different shadow effects, but from different angles. And if you collect all those different shadows and do image processing on all of those shadows together, you can figure out all the relative relationships of bone and bone-like stuff distributed through you. I should say X-rays do see tissue to some extent, but not great. So they're used to image tissue, but they're really good at bone. But if you just image from lots of angles and directions, you can figure out from shadow information, you can figure out what the spatial arrangement of all the parts was. It's a computing tour de force, but it's done anyway. Does that make sense? Questions? All right. So that's CT scanning. Those of you, if you've had a CT scan, it's typically like going inside a donut. It's a short. It's not very deep. It's just a ring that goes around you, and you hear whirring sounds as it's operating because it's actually moving the X-ray source and the X-ray detectors around you. It's going all over the place. It is using X-rays, and therefore it does involve high-energy ionizing radiation going through you. You do not want lots of CT scans. You don't want lots of X-rays either. They've gotten better at using smaller and smaller amounts of X-ray to form their images. They've got very sensitive detectors. Back in the day when they were using film, for example, as the X-ray detector, the film had to have enough exposure that it developed light and dark. But now they use devices that are much more sensitive than film, so they can use much lower doses of this ionizing radiation. It's not as damaging. But still, you don't want to go get a CAT scan every day. It's a lot of chemical damage to your body. All right? What if you want chemical damage? For radiation treatment, which alas is pretty common as well, it's used deliberately to kill tissue. Obviously, not tissue that you want to have around, like cancer tissue. And so the idea is you send in these very high energy photons. Gamma rays are then even beyond X-rays. I don't know where the threshold for one becoming the other is. But it's sort of in the vicinity of 1,000,000 electron volts. The energy that you'd get by accelerating an electron across 1,000,000 volt voltage difference. So they're very high energy things. They're very penetrating. They go right past most atoms, including, did we go through lead? Probably. So gamma rays are really cooking. They don't go easily through lead, I should say. You can probably shield them to a significant extent. But anyway, so they zoom along, and they cause a lot of damage. And the idea is to kill tissue with that damage. And often they're used from many different directions to target a small patch inside you. Suppose you got a bad spot, the size of this little lump here. You don't want to just keep zapping it from this direction because you'll zap a whole column of tissue. But instead, you zap it a little from here, and those only share one region in common. the bad spot. So you do a little damage to the whole column, but you keep hitting the spot you really want from all the different angles. You do primarily damage to it. So there's a lot of technological development trying to use gamma rays and relatives to gamma rays to target very localized regions from many directions so as to do as little damage as possible outside the region you want to clobber. So how do you produce gamma rays? So gamma rays are really high energy things. How do you produce them? You can still use Bremsstrahlung effects, but now you really, you can't just use a simple X-ray tube with a high voltage source. You actually have to get the electrons going really fast. You need high tech. You need an accelerator, which works strategically to get the electrons going faster and faster. They actually end up starting to move at close to the speed of light, and life gets complicated in working with them. But you get them going really fast and send them around a giant atom. You can get Bremsstrahlung gamma rays. The other is you use radioactive nuclei like cobalt-60 to emit spontaneously as they fall apart radioactively. They actually emit gamma rays because of radiative transitions, no longer among the electrons, but in the nucleus itself. The nucleus contains charged particles, after all, and you can get radiative transitions within the nucleus as it goes from different quantum standing waves to other quantum standing waves in the nucleus. Okay? So the sources then, for example, the cobalt-60 is a classic source of gamma rays because of these internal nuclear transitions and the electron accelerators. So that's how you make them. What do they do? Why do they do damage? Now they use two new effects that I haven't talked about before. They don't do photoelectron. There's not much Rayleigh scattering, not much photoelectron effect. There's just too much energy in these photons. They can't do radiative transitions, taking an electron out of the atom and sending it off at a modest speed. No, way too much energy. They instead do two weird things. One of them is the photon hits a single electron, and those two bounce off each other. This means that the photon behaves as a particle hitting an electron behaving as a particle, and they make this transition. That effect was not expected before the world of quantum physics, but it is now. With quantum physics, it's possible. It's called Compton scattering. So basically, an electron comes along, and a gamma ray comes along and just knocks an electron out of an atom, and the gamma ray continues on. It doesn't consume the gamma ray the way photoelectric effect does. It's one particle hitting another. They're both head off. So basically, the Compton scattering can happen many times. The gamma ray can come in and knock an electron out of this one, knock an electron out of that one. It creates just a whole shotgun of electrons flying off. And those electrons carry a fair amount of energy with them, and they can go do damage. So it's like shooting a bullet into a sack of bullets. Off it goes. So that's Compton scattering. The other effect that is even more bizarre is that gamma ray photon can go along, and in the vicinity of the atom and its electric charge, it can do something miraculous. It can materialize an electron right out of empty space. Poof! The gamma ray creates an electron. Charge has to be conserved, however. It's truly conserved in our universe, and so creating a negatively charged thing has to be accompanied by creating a positively charged thing. So it creates a positively charged version of an electron, which is known as a positron. It's the antiparticle equivalent of an electron. So a gamma ray photon in the vicinity of an atom, it needs the atom there to conserve energy and momentum properly. It can materialize what's called an electron-positron pair. It just rips them right out of the vacuum. A bizarre notion. The vacuum seems like it's empty space, right? No, it's a busy place. And this gamma ray photon can actually pull them out of the vacuum, one of each. They don't live very long. Positrons, being antimatter, as soon as that positron encounters an electron, they will annihilate one another. I'm thinking of the Da Vinci Code. Wait, it wasn't Da Vinci Code, was it? One of them, or one of those stories with antimatter. Ooh. You know, this is real antimatter. So during radiation treatment, they're making antimatter in you. Electrons and positrons, off they go, and when that positron encounters another electron, they explode. They disappear in a flash of gamma rays. So both of these effects, in long and short of it, both of these effects do a lot of local damage to tissue. They're both exotic effects, Compton scattering and pair production. Exotic effects that just really mess up the local molecular world and tend to kill tissue. Is that okay? Because gamma rays, apart from these effects, sort of just go right through you, they can treat deep-seated problems. Most of them go right through you and come out the other side. So they can work on killing tissue inches below your skin. All right, so that's the story there. What I do want to finish with, though, not to leave, is the other imaging technique, completely different. I mean, what it shares in common with what I just talked about is basically physics. So MRIs, what they're imaging isn't big, complicated atoms. It images the simplest atom, the hydrogen. In fact, the hydrogen nucleus. It's looking for protons. You can use MRI in its original, its parent, which is called nuclear magnetic resonance. You can use it on more complicated nuclei, but the one that is used overwhelmingly for medical imaging is MRI looking for hydrogen nuclei. And how do you look for those little guys, those little protons? They are magnetic. I told you before that the electrons, along with carrying a negative charge, they also have a magnetic dipole. It's as though they have a north pole and a south pole. And that is true of protons as well. They're also magnetic. It's got to be a dipole because, again, nobody's ever seen a pure single monopole in nature. So the proton has a net magnetic pole of 0, but it's got its north pole and a south pole. And if you put it in a strong magnetic field, or any magnetic field in principle, but a strong one in particular, they tend to align with the field. That is, they want the north pole in the field direction and the south pole opposite the field direction. It's like a little compass needle. Because of thermal energy at room temperature, it's tough to align those protons. You only get a little fraction more aligned than anti-aligned, even in a very strong magnetic field. But that's enough. I mean, thermal energy scrambles everything given an opportunity, and it turns most of the protons the wrong. You know, half of them if you just look at a random group of protons, half of them will be pointing this way, half of them the other way. And for quantum reasons, that they only have two choices. They're either spin aligned with or spin aligned opposite. There's some details here that I'll sweep under the rug. But basically, in a truly weak magnetic field, it'll be a 50-50 mix. In a really whomping magnetic field, like the kind in MRI machines, you get a few percent maybe that are more aligned with the field than anti-aligned. If you could cool people down to liquid nitrogen temperature, you'd do better alignment, but it would be hard on people. Okay, so you get them a little bit aligned, and then they interact with them with radio waves. What do the radio waves do? They flip these little compasses back the wrong way. If you get just the right radio wave, and the frequency matters, you have to pick it just right, you can actually reverse it. It's a quantum mechanical effect that it's either all or nothing, and that there's a specific frequencies you have to apply to flip it. But it is the case. And the result is they can put a person in a magnetic field. Let's start with it totally uniform. And if they adjusted the frequency of the radio wave, they would find in one precise radio wave frequency, all of the spins would begin to flip back and forth. And they would notice that in various ways. Wow, it's only absorbing radio waves, for example. But they don't put you in a perfectly uniform magnetic field. They put you in a magnetic field that's mostly uniform, but they can tweak it locally. They can put on gradients in the magnetic field. And now they can begin to interact with specific groups of protons. The ones, for example, if right along, right through my face, the magnetic field in that region is just right that for a specific radio frequency, they can flip those protons. They can now interact only with this slice of my face. Is that okay? And if they tweak things again so the magnetic field is just right to interact with the protons at that frequency, like this slice through my face, now they can work only with that. And if they do it again, so it's only this slice through my face, they can basically figure out one spot. They're now between those three measurements, one like this, and one like this, they can interact with one spot in the middle of my head. And they know that they've been talking to those guys, those protons. And so that's basically what MRI imaging is doing. It's using very clever techniques that work efficiently through your body. They can image, they can figure out what's going on with the protons in every little cubic millimeter inside you by working in slices through your various angles. And not only can they figure out sort of the presence or absence or relative amount of hydrogen atoms in every slice inside you, they can also detect the chemical environment of those hydrogen atoms. So they can tell, for example, if there's hydrogen in water, which is obviously much of the hydrogen inside you is in water, but there's also hydrogen in you in fat molecules, in other things, enzymes, proteins, whatever. And so they can start to figure out where all kinds of different things are located within you, but it's all based on looking for protons. Questions about those ideas? All right, what else did I want to say with that? With MRI then, you're in a strong magnet, which of course is an issue if you have any ferromagnetic stuff in you. So if you ever have had an MRI, first off, you got to take off all the metal. I mean, even conducting materials are iffy near these giant magnets, because we've seen that if you take a piece of aluminum, which is not intrinsically magnetic, if you try to move a piece of aluminum into or out of one of these super strong magnetic fields, you get current flow in the aluminum, right? Changing magnetic fields cause charge to move, and the current is magnetic, and it fights the magnetic effects that caused it. So it's hard to bring aluminum in, and it's hard to take aluminum out. If you drop a chunk of aluminum near one of these magnets, it will fall slowly, because it's struggling to deal with the currents that are induced in it. If you bring intrinsically magnetic material in, steel, now you're in trouble, because that will get sucked into the strongest part of the field, right? The field will magnetize it. It will then become strong field seeking. It will look for the strongest place. So this is why, if you've ever had an MRI, they ask you about, first, do you have any metal in or around your body? Have you ever been in a situation where you might have gotten metal in you by accident? Metal shavings, when machinists, for example, will have metal biddies in their fingers or something like that. All problematic. But okay, neglecting that effect, your body pretty much doesn't care about the presence of a strong magnetic field. Most of organic stuff is non-magnetic, so who cares? And the radiation that's used to interact with the protons and flip them back and forth is radio waves and microwaves. The photon energy is very small. It can't do chemistry. And so MRIs are pretty innocuous. As far as I know, there's no ionizing radiation. They don't damage molecules. So you can have MRIs every day for forever, and it's okay. Don't do CT scans every day for forever, because that's ionizing radiation. That accumulates damage. All right? We'll figure out something to talk about on Friday.